Namaste. Hello everyone, respected ma'am. This is Sarvagya Goel, 18MS008, and this is my assignment 6 of CH3101. And the topic that I have chosen for the presentation is the metal-metal bonding. First of all, I would like to start with acknowledgement, acknowledging the people who have helped me indirectly in this project, being it my family, my teacher, and my friends. So special thanks to all of them. So I'd like to start with the contents where I have listed all the topics that I have taken under consideration. First of all, I'll do some introduction about the chemical bonding, then the delta bonds, quadrupole bonds, the history and discovery related to the quadrupole bonds formations, the bright coloration of the complexes, as we have learned that these are very brightly colored complexes, then the role of the ligands in the formation of the metal-metal bonds, the clusters, which are the real life examples of the metal bonding and their applications and uses, and I'll conclude and then I'll end with bibliography. So let's start our topic and let's start with the introduction. So I'll start with chemical bonding because I think that everything we should start from the basics so that everything is clear for the basic itself. So we say that chemical bonding is the lasting interaction between entities. Entities can be ions, metal atoms, or simple other atoms, heteroatoms, homoatoms, molecules, so that they can form a compound or a molecule. And the bond that is being formed can be a result of electrostatic attraction, as in the case of ionic bonds, positive and negative charges, or it can also be due to the formation of covalent bonding or the sharing of the electron pool amongst the or electron clouds amongst the two atoms, which leads to the formation of, say, covalent bonds, metal Cs, etc. Now, there are different types of bonds that we come across. Whenever we are studying the chemistry, there are many different types of bonds. For example, sigma bond, pi bond, delta bond, hydrogen bond, banana bond, and many others. So they are a result of one or the other type of interactions taking place amongst them. So sigma bonds is the axial overlap along the axis head-on overlap, and the pi bonds that we talk about are the lateral overlap. So this is the formal introduction, so that everything is basically is very clear. So now here in this we see that this is an example of ethylene molecule that I have taken, and this so these are the set axes that I have defining an axis whenever we are making bonds, and whenever we are doing any molecular orbital thing, we always need to specify the bonds, and these are the bonds that I am specifying here. So this is the x-axis that I have taken, this is the z-axis, and this is the y-axis, which is across the screen which you are viewing. So this is the framework we have taken, where we see that these hydrogens and the carbon atoms are in a single plane. And there we see that the formation of single bond, where this is the head-on overlap between, so this carbon is sp2 hybridized, right? So this is one sp2 orbital, this is another sp2 orbital, this is the third sp2 orbital. So this mixed orbital, sp2 orbital with 66% p character and 33% s character, so they are the overlap, head-on overlap. So this is leading to the formation of cc sigma bond. This is leading to the formation of CH sigma, the 4 CH sigma with 1s orbital of the hydrogen. And then we have these orbitals, the extra p's in the carbon, which are doing a lateral overlap like this and like this here, and which leads to the formation of the pi bond. Now this is the example of the bonding that I have taken. So this is the Cl Na and the Cl, and it leads to the formation of the electronic exchange. They lead to the formation of Na plus and Cl minus, forming NaCl. This is the covalent bonding of one electron of hydrogen, the other one, they're overlapping with each other with bond of 1 and 2 electrons amongst each other. So this is leading to the formation of hydrogen molecule. And these are the metal bonding. So metallic bonding is a very special thing also. So I have not I'm starting with a formal introduction so that I can cover a diverse topic at the end. So this is the metallic bonding that we are taking into consideration, where we know that metals have a low ionization potential, so they easily get positively charged under the influence of thermal energy from the surroundings, or slightly heating up, or putting the H nu, the photonic light and all. So they get positively charged, and there is a pool of C and a pool or sea of electrons, as it is mentioned here, around them, and they interact with them, and they with a metallic positively charged metallic core and flowing electrons. So there are different types of bondings that we talk about. So now we talked about sigma bond, covalent bond, metallic bond. So now let's talk about delta bond. So delta bond is a very special kind of bonds that are the main topic of concern in my presentation. So they are the bonds which have four lobes being involved and they are being overlapped. So there are 4 points of contact that we talk about. So there are two nodal planes in the final molecular orbital, and the name delta arises from the d orbital because they're similar in shape. So how they are similar in shape, I'll show it in a video. It's a very pretty video, so that will give a nice better understanding of the shape and nodal planes of the delta bonds. So delta bond notation was introduced by Mulliken, and so this is the delta bond. So we see that these are the two these are the two d orbitals, this d orbital and this d orbital, and we see that the d orbitals have oppositely charged phases. See, these ones are same and these are opposite to them. So now this one will interact with this will interact with this lobe will interact with this one, and this one will interact with this one. So there are 4 actually points of contacts for forming the bonds between them. So this is the delta bond type, and finally it's look like this when the bond is the final molecular orbital that we form. So there is a small video. So wait a minute. Yeah. So I'm doing everything on phone. So this is a small video of the delta bonds. You can see. So we see here that these two gray things, this one, wait. So the gray balls that the pointer is not working here. So the gray balls that you can see are the nucleus, and the blue and the red ones are the oppositely charged, poles, or you can say the oppositely phased lobes. And there's a slightly white line intersecting the two nuclei. And they, if you see in a 2D, they look like a d orbital. So that's why they are named delta. And now clearly we can see that there were two delta bonds. So we can see that there were two nodal planes. One is this, and both are perpendicular to each other. So now the next slide is about the quadruple bonds. So quadruple bonds are the bonds in which there is a participation of 8 electrons. So there is 1 sigma, 2 pi, and 1 delta. So though we say that in this we saw that there are 4 points of contact, but delta bonds are really weak. They are weakest amongst the sigma, pi, and delta bonds. So the atoms need to be very close to each other to form such type of interaction. So when they need to be close, they already need a formation of sigma and at least 2 pi, so that they can easily interact with the lobes, and the distance between them, the bond length between them is such that the overlap between the two d orbitals is possible. So quadruple bonds were discovered by Cotton, by A.F. Cotton, F. Alfred Cotton, where he discovered them in the rhenium complex, where he had seen that the rhenium bond length was extremely slow. So this is the thing that I'm talking about. So the rhenium bond length was extremely slow. So since the since the rhenium bond length was extremely short, they thought that except for sigma and 2 pi, there should be any other type of interaction, there should be any other type of attractive force or bonding that is making them even closer to each other. So this was a thing that clicked their mind, and they finally led to the formation or discovery of delta bonds. And then, since there are 4 bonds that are being discussed here, that's the quadruple bonds. So they are usually seen in the organometallic species of the transition metals of different different transition metals, and especially the heavier transition metals. Heavier transition metals shows a large amount of metal bonding and quadruple bond formation. So quadrupole bond formation in the main group elements are unknown. So in the main group elements, that means not in the transition metals, but the S block, P block, so the main group elements. So the quadrupole bond formation is still unknown in them, but it's a recent paper by S. Sheikh and the group that suggested that quadrupole formation can occur in diatomic carbon, that is C2. So I'll again like to specify that I am a student of chemistry, and I think a good student of chemistry should not be focused or should not be just pinpoint to just one topic. There should be everything that is to be touched and and implemented in the experimentation and theory. So of course this is the CH3101 course, and this is the transition metal course, but I literally feel that uh, chemistry is interdisciplinary, and chemistry is a very versatile subject. So thinking that, I had put this point in this slide. So this is a C2. So we first of all, we hardly know the existence of C2, but C2 exists, and moreover there is a quadrupole bond formation between C2 which was not discovered before. It's a remarkable discovery, and it's a very recent discovery moreover. So this, I think this is a point worth to be mentioned. So we will talk about this more in the next slide. First of all, let me specify about the sigma and the pi bonds. So if we are taking the z-axis as the internuclear axis, so dz square is going to form a head-on overlap, head-on interaction, and which is going to formation of sigma bond. Then we have dyz and the dxz, and then they overlap laterally like this and like this, like this and like this. So they lead to the formation of pi bonds, and these two pi bonds are degenerate. And this is the dxy orbital, the dxy, and they overlap in the delta bond orientation, and they lead to the formation of delta bond. So we have not mentioned here that dx square minus y square. That must be a question that must be tickling to many minds. But the thing is that there is hardly any case where just metal is being existing. There's two metal atoms. No, there is of course a complex of the metal. There are ligands present surrounding the metals which are supporting actually the formation of quadrupole bonds. So there dx square minus y square is busy. So that's why it is unable, since its electron density is already being shared with the ligands, it is unable to participate in the formation of delta bonds. So that's why it's quadrupole. That's why no 5 bonds are usually seen in such scenarios. So this is what I was talking about. So the history and discovery related. So this is Mr. Cotton, Professor Cotton. This is the citation of the Mr. Cotton's paper. And this is the Sheikh and his group, ETEL. All these people, they all discovered about the quadrupole bonding in C2, which have analogous H valence electrons. So this is a very nice thing. This is a very nice discovery, and it's a very recent one. So let's look into this small video. So this video is related to the quadrupole bond formation. So this is a previously unseen phenomena of bonds between the rhenium metal. Yeah. So you can see there are two dark colored entities there. These are actually two rhenium, this is a pair of rhenium metal atoms. They are breaking continuously and reforming continuously. So this is a work done in New York by the researchers using high resolution TEM, transmission electron microscopy technique, to see the real life scenario of the real life video of the formation of metal bonding. It's a nice video that I got, so it was a must to be included. So these are the people. So I hardly put any people in the presentation, but I think these people are worth mentioning. They have created history. The formation of quadrupole bonds has led to the formation of clusters, and clusters have wide applications in the field of chemistry and science. So this is Mr. Cotton. This is Professor Cotton, and this is Mr. Sheikh, who has actually done research along C2 and inorganic quadrupole bond formations in the main group elements. So this is the energy profile of diagram of the metal with the two metals are interacting with each other. So this one here we see this is the sigma bond. Wait. So this is the sigma bond, and this is the pi, this is the delta. That's the delta star, pi star, and sigma star. So sigma is the most stabilizing one. So the sigma star will be the most destabilizing one. The antibonding character will be maximum in energy. And we see that pi is weaker, is less strong as compared to sigma bonds. So it is less split. And delta bonds are the weakest bond. Though they have 4 points of contact, but the interaction is not as good as in sigma and pi bonds. So here the splitting is minimum between them. Now this is the energy profile diagram where we take 5 degenerate orbitals of 1m. This is m and this is another m. And this is an M2 molecule, just an M2 one. So there we have a dz square. Along dz square we have 1 sigma. Then we have along pi xz and yz. Then along delta we have xy, x square minus y square. So we see that this is the molecule where we have 5 bonds amongst the metals, and this is the energy profile. But once there is a presence of ligands, the dx square minus y square, which was initially forming a delta bond and giving this split, is now actually giving a different split because of the formation interaction with the ligands. Now it is not forming a delta bond. There is just one delta bond which is being formed among the metals. This is the thing that I was saying, that there are very less cases in which there are 5 bonding taking place between the metals. There is a ligand supporting it. So that's why there is always or usually 4 bonds that takes place instead of 5. And since delta and delta star are the delta is the weak bond, so delta star is also not much higher in energy. So the difference of energy between these two states is very less, and it usually lies in the visible spectrum. So this is the next topic that I'm going to discuss about the coloration of the complexes. So this is another thing that came into my mind, and that is the topic color that I chose to write the topic, the bright coloration of organometallic complexes. So of course I have not used any bright color to write this topic. The simple reason being that I want to specify that what is the role of bright coloration. So bright colorations are very eye-seeking. They can be used as probes, they can be used as dyes. As in the case of probes, they can also be used in human bodies with less toxicity if their toxicity can be controlled, and also in non-biological systems also. So I have chosen this, that might seem funny, but I have chosen a slightly dull color, to write this topic, because I want to tell that always bright colors are eye-catching, they are easy to learn, they are easy to read, they are easy to observe, and they're easy to give a proper and apt conclusions. So there's a very integral role of bright colors in our lives, and in the sciences also, when we use, for example, say litmus paper or anything related to color transformations that take place. So they're very important for us to study. So there is a homolumo whenever we are talking about coloration, that is due to the absorption and the emission spectra. And when we talk about absorption and emission spectra, there is excitation or de-excitation. And when there is excitation or de-excitation, there is always a talk about HOMO and LUMO. So this is what we are going to talk about, the HOMO and the LUMO. So if the highest, or if the HOMO is highest occupied molecular orbital is delta, and the lowest unoccupied molecular orbital is delta star, then we know that the energy gap between them is so low that the transition taking place is in the visible region, and then there will be of high and bright coloration. So that is the thing, that is the theory behind their bright coloration. So they are transition metal complexes with quadrupole bonds, are brilliantly colored. So this is an example that where we have taken different ligands, and we have taken different metals, different configuration of the metal, and we see different color of the metal depending upon the ligands, and also the number of metal atoms that are in the complex. I'll tell you with a picture in the next slide. This is the paper related to it, so I have quoted the paper here. So I have gone through it, you may also go through it. So this is about the effect of coloration taking place when the different ligands are used and when different number of metal atoms are used. So here we are. So this complex has just one MO, this MO. So this is just one molecular orbital, sorry, one molybdenum that atom. This complex has two molybdenum atoms, two metal atoms, but there is just single bond between them and rest bonds is busy with the ligands. This one has a quadrupole bond formation. Of course, there are multiple bonds between the metal atoms, but the ligands attached to them are weak. We know that chlorides are weak ligands. And this is another scenario of molybdenum where we have a stronger ligand with respect to chlorine, the phosphorus ones. Okay. So the observation here is that this complex is colorless. This complex is pale. And these two complexes are brightly colored, with this one being more brightly colored and with of lower energy range. So why is this so? So I think that's very easy, and that's very easy to guess even. So this has no delta bond formation. There are only sigma bonds formation taking place, and the transition in the sigma bond formations and the splitting is slightly difficult as compared to the delta bonds. Here we have a sigma bond, so it's pale colored, but still the effect is not as strong as it is here and it is here. So here we have multiple bonds, here we have delta bond formation, here we have transitions taking place from delta to delta star, which has the energy range given in the visible region and slow. So they are, both of them are brightly colored, though the effect is being seen with respect to the change in ligands. So this is the so this is the thing, this is a picture of bond order. So this is 3, 3.5, 4, 3.5, 3. So here the electrons are being filled in the bonding orbitals still here, and then the electrons are going to fill the anti-bonding orbitals. So here we see that the transition, if there is an excitation, it will take place from pi to delta. Here the excitation will take place from delta to delta star. Same is the case here and here. And then this one, if there is any transition, it will take place from delta star to pi star. So what is observed is that these three complexes where there is excitation from delta to delta star are brightly colored, and these two ones are not as brightly colored as these three. The simple reason being the gap between the delta and the delta star is lower and as compared to the other cases, and that's why it is allowing it to give a good and a nice color to the solution or the crystal, that if we are able to crystallize it. So role of ligands. So ligands are very, they are the very important part. Like if you serve a plate, you need a spoon. At least I need a spoon, some do not. Okay. So if, for example, if you need a plate, you need a spoon. So you need some things, they go hand in hand. The same thing is with the complexes and the ligands. Whenever we talk about complexes, there is always an integral role of ligands. You can never ever neglect the role of ligands there. So the valence ionization, so there is a change in the valence electronic configuration and the valency features and the ionization features when we talk about the ligands. So there is an experiment that was done, and this is the experiment I am talking about in the helium-1 photoelectronic spectra. So they took different compounds for metal which was nitrogen rich. That is, they were the ligands had the donating atom as nitrogen. The same case is the Cy-form here. Cy-form is also a different ligand, but the donating atoms are nitrogen. So they found that unlike in the case of high electronegative ligands, which are electron withdrawing and which are electron withdrawing and they don't have high electronegativity, so they don't impart much electron density to the metal center. So their cases, it was seen that the formation of delta bonds was not as delta bonds, quadrupole bonds, or metal bonding, you can say, was not strong or was not as strong as in the case of the more donating ones, as in the case of nitrogens. So we have seen that there is a influence of the ligands where the more donating ligands are basically making the metal atoms push close to each other, helping them to come in the proximity of each other. And we have discussed in the starting itself that the metal atoms need to be very close to each other to form the delta bonds, because they're very weak interactions. So this proximity is actually also brought about by the ligands. So ligands have a very important role to play in the formation of quadrupole or the delta bonds, or even in the metal-metal simple bonds. So this is the picture that I have taken from Mizler and Tar book, and I think this is worth it because I searched, I think I searched a lot for a similar pic, but I couldn't find one, and this pic summarizes everything in just one go. So I'll start. So this is the bond length which is being discussed about, CR distance, the bond length. So here we see that there are no such much donating atoms, atoms in the ligands. So this bond length has a particular value, say 183.5 picometers. Now in this case, these are 4 nitrogenous ligands. There are 4 nitrogen atoms attached to it, and we see the decrease in the bond length to 180.3 picometers. And again, if we take more number of nitrogen atoms, 1, 2, 3, 4, 5 and 6. So if we take again 6 nitrogen atoms, here there were no 1, here there are 4, here there are 6. There is a further much decrease in the bond length, which is 174.0 picometers. And this is the same, this trend easily tells us that with the increase in the donation capacity of the ligands, there is much closeness or much push is there amongst the metal atoms, so that they can come close to each other and they can form bonds. See, whenever there is a decrease in bond length, we always say that there is increase in bond order. They are inversely proportional to each other. So this thing we have learned, I guess, in 11th. So bond length is inversely proportional to bond order, because as the bond order increases, the atoms comes close to each other and the bond length decreases. So the same thing is here. We just have to, reciprocate it. Since the bond length is decreasing, we can observe bond length, right? We cannot observe bond order. Bond order cannot be observed. You won't see, nobody will see, in fact, bonds between them. But what we can see or what we can measure is that the bond distance. So this bond distance, as it decreases, that means there is more interaction amongst the metal, and that interaction is coming due to the change in ligand from here to here. So that specifies that the role of the ligand here, which is making the metal atoms come close to each other and form a better metal-metal bonding. So this is another example in which I have taken the discovery one. This rhenium complex Re2Cl(A2 minus) was the one which Alfred Cotton took, and in which he discovered the formation of quadrupole bonds. So this is has a very low bond length. So the bond order here is 4. There are 4 bonding and 4 anti-bonding here. These 4 anti-bonding molecular orbitals, right? So, and we know that Re here has D4D4 configuration. So here, when we start filling the bonding molecular orbitals, the sigma, the pi and the delta, all of them are occupied, and all of them give rise to the bond order of 4. So we discussed here bond order 3, 3.5, 4, 3.5 and 3, because 4 is the maximum possible bond order. And you see, when configuration has achieved its maximum possible bond order, this configuration, that means it will have the minimum possible bond length. So this is the reason for the discovery of the discovery of quadrupole bond, the discovery of delta bond, which Cotton did, because they found that the rhenium bond length is exceptionally small. They did not expect this much, that something is wrong, right? This much small should not be there. So that was the intuition that took them to this discovery. So this is because of the bond order that we are talking about. And chloride, of course, has a role to play here, because chloride is also electron rich, and its electronegativity is in comparison with nitrogen. So this, we can take them analogous to each other. And so they led to the formation of, along with the role of ligands, we also see that the bond order has a very important role here, which led to the formation of the quadruple bonds. So these are via the simulations they have created what is the exact look of the, or a final molecular orbitals respect with to the respective symmetry. So this is a very important change that came in science with the chemistry science, basically with the formation of quadruple bonds, and this was due to the exceptional small bond length. Here, the exceptionally small bond length was the root cause was the quadruple bond formation, and the quadruple bond formation was led by the chloride ions as well as the maximum possible bond order. So this, whenever we do any experiment in our daily lives, or whenever in a lab or something, so we always need to work on the best possible specimen or the best possible, system. So this is the best possible system that they chose, and that is why it was a success. So that's also a very important part in experimentation and application. So next is clusters. So I told that there is hardly any case where there are just two M2, just two metal atoms interacting with each other. Of course, there is a support of ligands, and their metals are surrounded by the ligands, and then is what we get a functional unit. So clusters are actually the functional or the real life, the real life scenario of the metal-metal bonding as it exists. So in chemistry, a cluster is, a group of atoms and molecules which are definite in number, definite in geometry, symmetry, and shape, and they are specific. And they have a very, wide range of applications in our daily lives also. So transition metals and main group elements both from robust clusters, and but usually we have, a metal center. So whenever in layman terms, whenever we say cluster, we always assume it's a metal cluster. So here we have a different types of ligands. Here we have a different types of ligands that support the formation of clusters, and there are a wide variety of bonds that can be present in a clusters, like with the metal and the monodentate ligand, the bridging ones, and the metal-metal bonding, and there are many different types of bondings that can take place. So this is an example of where the 5 bondings are taking place. It's not quadruple. Here bond order is not 4, it's 5. So here there are 2 delta. Here there are 2 delta, 2 pi, and sigma. So this is a very rare case, very rare scenario. This is the real scenario that exists. So this is a rare case, or you can say the experimentally generated one, and which you can say has less lifetime, or you can't expose it to many stress conditions. So like temperature or room temperature or pressure. So these are under, under specific conditions that they are being synthesized. But this is a real life scenario. It looks like complicated, a web-like structure. But this is a structure of MnO4O5Ca cluster. So this is an oxygen evolving complex of photosystem 2. So this cluster actually converts water to O2 in our atmosphere. This is a natural cluster. This is not a artificially generated one. So this is the real life scene that this is how the clusters are actually. You cannot have delta bonds with 2 delta bonds because ligand is very important. So there are a few videos that I would like to discuss and show. So this is the platinum, platinum in the cluster with the catalytic application. I'll play it again. It's a small video. I have tried to keep the videos small so that I can cover them in the, in a short period of time, and I can actually relay the thing that I want to relay. So these are the countings of the number of platinum atoms, and this is a catalyst. So there is another video that I have. So this is another cluster. So the center one here, the golden colored thing, is actually a gold atom, Au, and the yellow ones that you see are the chloride atoms, and the rings are the phenyl groups basically, and the slightly bluish and silver like color is actually the silver atoms. So this is a cluster of silver. This is a nano cluster basically. So this is a nano cluster of silver and gold. So this is a unique example because here we see metal metal bonding between the heteroatoms. So usually what happens in that is that whenever we form clusters, is they are usually formed by there is slow nucleation, and then there is fast aggregation. And if the aggregation is maintained, then it can be a nanocrystal, or it can be a large crystal if it is not maintained with different applications. So this one is a heterocrystal. This is a heterocrystal of gold and silver. So there are very slight cases where we see a heterocrystal. We usually see homocrystals of same metal atoms. So this is a unique example. So that's why I think it's very important to specify it. So this is possible and this exists. So this is a catalyst basically. So I'll like to take it to the next step, the applications and uses. So I think the science that we learn today is for two reasons. One is the curiosity. I think human is the most curious species on the earth, or I don't have experience in others. Okay, so I think but we are very curious. At least the students and the children, and at our age, we are very curious. And I think human species, as a whole species, is very curious to know everything, to learn everything, to try everything which is new and adventurous and exciting. And the another thing that we do science is for, it's making our lives more comfortable, making making us feel better, or making us feel more lively in our surroundings. So that we can have a wide variety of compounds and systems or machineries which have apt uses and applications. So this topic would of course be very very incomplete if I don't talk about its application. So applications of metal metal bonding and clusters, and quadruple bonds, delta bonds, it's a very important part. So I'll discuss it with this. So the first point says about the magnetic properties. So magnetic properties, so let's take an example. So for example, it's a D3 system. So one metal atom has a D3 configuration and has three electrons. So if it has three electrons, we very well know that it has to be paramagnetic, right? So the same, excuse me. Yeah. So the same is the scenario with the next metal atom. So it is also D3 configuration. Now, when these two D3 these two metals of D3 configuration, if they come together, what will happen? So they will form sigma bond, and if they form two pi bonds, and let's make the steps. Sigma, 2 pi, delta, delta star, sigma, pi star, 2 pi star, sigma star. So now each has 3 electrons. So total number of electrons are 6. So when there are 6 electrons, so what will be filled? The sigma will be filled, and the two pi's will be filled, and the delta and the rest of them will be empty. So what will happen is that the two D3 atoms who were actually paramagnetic earlier, they were not coupled. We know that with the maximum multiplicity, they all were single, and they were not coupled with each other, and they were paramagnetic in nature. And now when they are brought together, they lead to a diamagnetic species. So that's a very drastic change, right? From a paramagnetic to a diamagnetic. So these are wide applications when you talk about the change in the magnetization, or if you want some other changes, your system is such that you want to change the magnetic field around it. So in that cases, with slight modifications, with slight change in the bond distance between the two atoms, you can change the scenario or the external environment that you might be providing to your system from say paramagnetic to diamagnetic. Okay, so this is another example. This is a paper basically. So this is a paper which talks about that the chromium quadrupole formation leads to enhanced paramagnetism. So this is the paper that I have quoted here. You may go through it. So the paramagnetism here is increased, is enhanced. So it has also wide applications. You want to learn the hysteresis curve of the paramagnetic changing from a diamagnetic situation, or your experiment requires a high amount of paramagnetic environment, but you were unable to provide because you didn't have something like that earlier. But now, due to chromium quadrupole bond formation, we see the formation of paramagnetic species. Paramagnetism is observed. So there are change with the change in the properties, with the change in the bond distance and the change in the properties, you can actually change the magnetism. So this is the same thing that I have mentioned in the next point. So it's the ionization energies with the change in structures, magnetic properties, and main things of, many things are evolved, many properties are evolved as there is changes in the sizes and the distances amongst the metal atoms. So earlier there were very less number of complexes and the metal complexes that were possible, but now there are a very large number of chemical and unusual structures which are very interesting and which have very important uses in our daily lives. So there are different types of clusters and different types of metal complexes that have different types of activities, and they can mimic the behavior of different types of substrates or the natural chemicals or the substances that were present earlier. So this is again a nice video, so let's go through it. I think it will be very nice. So this is talking about the stability.
First discovered in ancient times, metal nanoparticles seem to find new applications every day. However, scientists are relatively far from being able to engineer new nanoparticles for specific applications. Towards engineering nanoparticles, tiny metal nanoparticles, called nanoclusters, have recently attracted study due to their atomically precise character and remarkable stability. For example, the thiolated 25 gold atom cluster shown lasts for years at room temperature. Traditional thoughts surrounding this remarkable stability have centered on electron counting methods. However, several other nanoclusters exist that do not follow these rules, leading to a need for a new theory surrounding the thermodynamic stability of these nanoclusters. To start thinking thermodynamically, we must first think of an initial state where the components of the nanocluster exist in solution immediately following a reduction reaction, treated as a combination of free metal atoms and metal thiolate compounds. Then, over time, the nanoclusters form in solution. So we look to the formed nanocluster as the final thermodynamic state of the same initial components. In the formed nanocluster, the chemical potential difference between the initial and final states of the atoms in the nanocluster would therefore, in part, dictate the thermodynamic stability of the nanocluster. An imbalance in chemical potential would favor rearrangement, while of perfect balance, a stable cluster. Thus, a perfect balance should exist for all reported atomically precise nanoclusters. And this new thermodynamic stability theory should be a step towards engineering atomically precise nanoclusters and could have implications in other nanomaterials.
So this is a very nice video. So this video actually tells about that it's easy to say than to do. So easy said than done, right? So there we talk very easily about clusters, we talk easily about nanoparticles, we talk easily about bringing the two metals close to each other, but actually there are many challenges that we might face. So this is one of the videos that where the scientists faced the thermodynamic stability challenge and they overruled it, they overcame it, and then they finally made a highly stable thermodynamic complex, so which could at least survive for 4 years. So having a complex which has survival times in seconds or in minutes, so having a one with survival time of 4 years, the second one is much better. So there are challenges, but there of course I think that there is no question which cannot be answered. It might be a different scenario where the person doesn't know the answer, but there is no question which is unanswered or which cannot be answered in this world. So this is one of the video that talks about the real scenario where the real challenges and the real way to increase the thermodynamic stability and the priorities that we need to make while forming a nanocomplex, because nanocomplexes is this is an era of nanoparticles, and metal bonding leads to very stable nanosystems. So like we talked about here of gold. So the expense is something different, but the stability is the priority as we work as scientists. So of course, for the industrial use, if you want, you also need to see the expense. So the earlier the scientists were actually here only, but now we see that scientists have actually moved far, and they are actually dictating over the different properties that are required for the complex to be stable. So this is a cluster surface analogy which talks about the function of the clusters as catalysts. Clusters are a very important part, have a very important role as catalysts. So they can act as solid catalyst, and they function through the cluster surface analogy. Many different types of data can also be interpreted due to this, and they can be either homogeneous or heterogeneous catalyst. That depends upon actually the reagents or the solution mixture. If the reagents are solid, then of course it's a homogeneous catalyst, because the catalyst is also solid and the reagents are also solid. But usually it happens that the catalyst is different. The catalyst is solid and the reagents are either liquid or gaseous, mainly gaseous. So it leads to the formation of heterogeneous catalyst, and the catalyst is heterogeneous catalysis. So this is the formation of cluster surface analogy. So this is another examples of the application. So this is a system in which, where we, with providing some temperature, we can convert water and carbon monoxide to hydrogen gas and CO2. A very wide application. So this is again a metal complex of MO5N6 catalyst, molybdenum and nitrogen. So we see molybdenum, the MO5 means there is metal bonding existing between them, and nitrogen is specifying that it's a good electron donating group, so there is high chances of and stronger formation of metal bond, or molybdenum bond. So we know that carbon monoxide is a very important, no, I would say, a very integral part of the industries, the fuel burning, the incomplete combustion of vehicles and all. So just in the presence of water, moisture is a very common thing that we find, in atmosphere, or even in the reactions taking place in industries or the fuels. So with their reactions, with just an apt catalyst like this, we can convert it into CO2, which is less which is less harm causing as compared to carbon monoxide. And hydrogen gas, it has wide applications. You can use it widely for reduction purposes and other purposes. So this is such a great work. So this is something which is which tells about the power of this metal bonding. So this is another example of hydrogenation, where we see that metals like iron, cobalt, nickel, copper, and platinum, they can actually convert a unsaturated compound to a saturated one by adding hydrogen atoms to it, and they can do hydrogenation on the surface. So this is another example of hydrogenation. So why I've mentioned is that because I earlier also I mentioned that we want to sometimes invent something and replace the former one, because the former one is either inefficient or expensive or toxic, or it may have some disadvantages attached to it. So here what happened is that earlier for hydrogenation, rhodium complexes were used. So what happens in the rhodium complexes is that rhodium is actually a very rare metal, it's very precious, and this reaction led to a very high expense. So you cannot perform this reaction in large scale in industries. You need some better thing, you need a better catalyst so that it has the higher efficiency, or at least the same efficiency, and it is also cheap. So here we saw that simple atoms, iron, cobalt, nickel, we easily use them in alloys, right? Copper, so cheap metals, we can easily use them for the process of hydrogenation. We do need not go for such rhodium complexes, and making such this whole process a very expensive one. So this is the use, this is the benefit of formation of clusters. So here we saw that rhodium is this is a lone metal, and here they are the clusters. So this is the real life use of metal bonding, which leads to the such a beneficial thing on the on the expense and the economical scale. So there are different types of shapes and different types of ligands, and these lead to the formation of different kinds of stereochemistry. And we all know that stereochemistry is very important, very important, especially when we talk about biological systems. We can never ignore the stereochemistry R, S, D, L. Excuse me. Yeah, so we cannot ignore the stereochemistry of the system, the final molecule when we are injecting it into a human or any biological system. So the slight changes can make big changes in the long run. So that's why clusters are very, very important. Or you can say the metal-metal bonding interaction is very, very important. So they can do chemisorption, physisorption, and this can lead to different types. Hydrogen diffusion, the hydrogenation is also one of the same thing. Distortion can lead to interstitial heteroatoms. There are wide range of applications of the physisorption and chemisorption in the chemical world, and these clusters are very, very efficient in them. So now they can be used to study the reaction mixtures at the metal centers, and they can be used for mimicking the elementary processes. So mimicking elementary processes are very important when we want to synthesize something artificially. So when we sometimes, we need sometimes to synthesize artificially, and for that it's not possible that we always provide the natural environment when we are preparing some artificial compound and not in the body itself. We are preparing something in vitro and not in vivo. So for mimicking the system, we need some efficient and better catalysts which can work efficiently in the in vitro system. So there also the clusters are very, very important, and they can also tell us about the reaction mechanism with the help of the metal centers and the interactions. So they play a different types of important roles like condensation, evaporation, adsorption, etc. And this is another recent thing that this is a paper that I have came along, that the catalyst can absorb sunlight to make chemical fuels, which will have central role in the future build of sustainable energy. A very, very remarkable thing. So what it tells about is that such catalysts with metal-metal bonding interactions, they can absorb sunlight and they can make such chemical fuels which can actually can be renewable and or can be cheap and can be more sustained in the future. So these are the stepping stones. Each discovery in science, whenever there is a huge discovery in science, it always has a supporting background of many, many years of hard works of many, many different labs, scientists, groups, and many different types of fundings. It's not always the alone that discovery, there's never ever a case where a discovery started from scratch and it has gone to the maximum peak possible. No, there are always papers related to it, there are always backgrounds related to it, which is the hard work of many scientists being done in the past. So this is a very important thing. So whatever we are learning today and whatever the scenario is today in 2020 as of now, this place, this time, this second, this might lead to some some big change, a big discovery or big invention in the future, and this might be a stepping stone. So this is the thing that once we saw, like for example here we saw where carbon monoxide was converted to carbon dioxide. So this was again a remarkable discovery. So this can again lead a better future. So these are the things that we should always keep in mind when we study and when we look the world with our eyes. So these are small videos. I'll go through it. Very interesting. It's very nice application.
Catalysts are currently used in the chemical industry to reduce the amount of energy needed for a particular chemical reaction to proceed. So they can be both a time and money-saving device. A potential new source for catalysts in industry is metal clusters, which are groups of between 2 and 100 metal atoms bound together with unique properties. In my research, I'm looking into the fundamental electronic properties of these clusters, which can go on to determine which will be the most efficient catalysts. An example of how these clusters can be used is converting carbon dioxide into liquid fuels, which can both reduce CO2 emissions and form part of the solution for the world's growing energy demands.
So this person is doing a great job. So what his experiment is about converting CO2, the emitted CO2, which is a very potent greenhouse gas, to something liquid fuel, so that its toxicity can be slowed down and can be easily, it can be easily waved off and it is not as polluting as it is in the case of in the gaseous form in CO2. So this is another video. So these are the applications. So this video is about text. So I
Capture and convert. This is the motto of carbon dioxide reduction, a process that stops the greenhouse gas before it escapes from chimneys and power plants into the atmosphere and instead turns it into a useful product. One possible end product is methanol, a liquid fuel, and the focus of a recent study conducted at the U.S. Department of Energy's DOE Argonne National Laboratory. The chemical reactions that make methanol from carbon dioxide rely on a catalyst to speed up the conversion, and Argonne scientists identified a new material that could fill this role. With its unique structure, this catalyst can capture and convert carbon dioxide in a way that ultimately saves energy. They call it a copper tetramer. It consists of small clusters of 4 copper atoms each, supported on a thin film of aluminum oxide. These catalysts work by binding to carbon dioxide molecules, orienting them in a way that is ideal for chemical reactions. The structure of the copper tetramer is such that most of its binding sites are open, which means it can attach more strongly to carbon dioxide and can better accelerate the conversion. The current industrial process to reduce carbon dioxide to methanol uses a catalyst of copper, zinc oxide, and aluminum oxide. A number of its binding sites are occupied merely in holding the compound together, which limits how many atoms can catch and hold carbon dioxide. With our catalyst, there is no inside, said Stefan Vida, senior chemist at Argonne and the Institute for Molecular Engineering and CO author on the paper. All 4 copper atoms are participating because with only a few of them in the cluster, they are all exposed and able to bind. All exposed and able to bind. They are all.
So there are not much pictures in this video. I completely agree. There are 2-3 pictures only which are being rotated continuously. This is because this is still a hypothesis. It has not been applied. I have gone through it. There is a paper related to it. I have mentioned it in the bibliography. So these are the golden colored 4 class. The tetramer like structure here is the 4 copper atoms, which are actually catalyzing the conversion of CO to methanol. And we know that methanol has a wide applications in the industries also, and in the labs also, for cleaning purposes and all. We use it for sterilizing. In the sanitizer, this is the corona era, where corona everywhere, it's there. So for the hand sanitizers also, there's a slight concentration of methanol which is being used. So this is this is like something converting a completely useless thing. Extra CO2 is very important, but extra CO2 is completely useless, right? So completely useless thing like extra CO2 to completely useless thing like methanol. So this video talks about them. It's still their theory. They have a hypothesis. They are not able to implement it to their fullest. But I think these are stepping stones, and the stepping stones always lead to success, and we will succeed someday. So this is the theory which has been proposed by these scientists. So these were the links. I have mentioned them. So now I think I took a lot of time of you. It's nearing 1 hour. So I'd like to conclude by saying that the delta bond formation, the quadrupole bond formation, the metal-metal bonding interactions, they have actually, and finally the formation of clusters, which are the real life, scene of the metal bonding. So they actually have a very vast application in this era. And I think it can even turn the theories upside down, or it can create some new discoveries, theories, and inventions in the forthcoming years. And I really feel proud that I chose this topic. So this is the bibliography. So these are the various sites and links that I have referred to. So these are the papers. These are the papers. These are the I have actually consulted many sites, many links, but these both of them, these slides signify the links and the citations which I have consulted, and I have put at least something in my slides, so in my presentation. So this is that stuff, and so this has indeed given me a lot of information and knowledge, and I think it has also increased some information of yours. And I'd like to thank you, ma'am, for this opportunity so that we could make this. And I'd like to thank everyone who has helped me, as I have mentioned in the acknowledgement. One more thing that I have mentioned in the acknowledgement, and I would like to mention it again, is that this is the second time that I'm presenting in my life, I guess, since ICER. So, with a presentation. So, the first time was last year. Of course, it was offline mode in front of teachers. And this is the first time I'm presenting in the online mode. So, this is my first online presentation that I have made, and I'm presenting to someone. So, and that too, it's such a wonderful topic. I think it's a topic full of essence and vividity. So I really will always cherish it, and it will always be remaining deep in my heart because it's in one of my initial days of my life. I know that presentation is a very normal part of your life, the life of the professors and the teachers. But this is indeed presenting. This presentation was indeed a very special moment of my life, and I loved it. So thank you so much. Thank you everyone. If anyone else is listening, and thank you, ma'am. So yours faithfully and sincerely, Sarvagya Goyal, 18MS008. Namaste. Thank you. Bye.